Right now, a machine floating 1 million miles from Earth is rewriting everything we thought we knew about the universe. The James Webb telescope just captured galaxies that formed 290 million years after the Big Bang, black holes heavier than entire galaxies, stars exploding at the edge of time itself. We are seeing light that has traveled for 13 billion years to reach us. You are about to witness discoveries that challenge the very laws of physics. If you are ready to see the cosmos like never before, hit that subscribe button. The journey begins now. "1 million miles from Earth, a machine the size of a tennis court hovers in the darkness. The James Webb telescope cost $10 billion and took 20 years to build. Its mirror unfolds like origami in space. 6 hexagonal panels made of gold-coated beryllium catch light that left distant galaxies when the universe was an infant. This telescope does not orbit our planet like Hubble. It circles a point in space where gravitational forces balance perfectly. Scientists call this the second Lagrange point. Here, shielded by a sun shield the size of a tennis court with protection equivalent to sunscreen factor 1 million, Webb stares into the infrared spectrum. Why infrared? Because the universe is expanding. Light from the most distant galaxies stretches as it crosses space. By the time ancient starlight reaches us, wavelengths that started as visible blue and ultraviolet have been pulled into the infrared range. Hubble could never see this. Its visible light cameras went blind at a certain distance. Webb sees what Hubble could not. The telescope launched on Christmas Day 2021. For 6 months, engineers held their breath as it deployed. 1,044 things had to work perfectly. A single failure would doom the entire mission. Every panel unfolded without error. Every instrument activated flawlessly. Then Webb opened its eye and looked deeper into time than any machine in history. Each observation is a time machine. When you see a galaxy 1 billion light years away, you witness that galaxy as it existed 1 billion years ago. The light took that long to travel across space. Webb pushes this principle to its absolute limit. The telescope captures photons that began their journey when the universe was less than 5% of its current age. These ancient galaxies appear as faint red smudges against the cosmic darkness. Their light has been traveling for more than 13 billion years. We are not just seeing distant objects. We are watching the birth of the cosmos itself. Scientists thought they understood what early galaxies should look like. Small, faint, and simple. The universe was too young for anything complex to exist. Webb shattered those expectations in its first week of operation. The galaxies it found were wrong. They were too big, too bright, too mature. Some had already formed massive structures that should have taken billions of years to develop. One astronomer called it completely unanticipated. Another said it might break cosmology. The standard model of the universe predicted one thing. Webb showed something entirely different. Every image revealed galaxies that challenged decades of theory. Every spectrum told a story that did not fit the textbook narrative. What happens when your best instrument shows you the impossible? You keep looking. And what Webb found next was even stranger. The galaxy appeared as a tiny red dot in Webb's first deep field images. Astronomers labeled it with a catalog number and moved on. Then someone ran the numbers. The light from this galaxy had been stretched by a factor of 15. It existed just 290 million years after the Big Bang. The universe is 13.8 billion years old. This galaxy formed when reality was only 2% of its current age. Call it jades. Scientists stared at the data for months. Convinced they had made an error, they rechecked everything. The measurements held firm. This was not a mistake. Jade spans more than 1,600 light-years in diameter. It glows with the light of forming stars. The galaxy is bright enough that Webb could have detected it, even if it were 10 times fainter. That means other galaxies from this era are waiting to be discovered, perhaps galaxies that formed even earlier, in the first 200 million years after creation. Here is the problem. Standard cosmology says galaxies grow slowly. They start as small clumps of matter in dark matter halos. Gravity pulls in gas. Stars ignite. Over billions of years, galaxies merge and grow massive. Jades did not follow this script. The galaxy is too luminous, too organized, and too large for its age. Computer simulations predicted early galaxies would be dim, chaotic, and tiny. Jades is none of these things. It radiates light from young stars, not from a black hole. That makes it even more puzzling. Black holes can produce tremendous brightness from a small region, but star formation requires time that Jades should not have had. Other early galaxies showed the same pattern. They were bigger and brighter than they should be. One astronomer described it as finding a fully grown adult where you expected to see a newborn infant. The universe simply did not have enough time for these structures to form through conventional processes. Some scientists proposed that galaxy formation happened faster in the early universe. Perhaps stars formed more efficiently back then. Maybe dark matter halos collapsed more rapidly. These ideas help, but they do not fully explain the observations. The galaxies are still too extreme. Another explanation involves what astronomers call initial conditions. Perhaps the Big Bang did not spread matter evenly. If certain regions started denser than others, galaxies could have formed faster there. But this raises new questions. Why would those dense regions exist? What process created them? The discovery of Jades extended our view into cosmic history by 40% in just 18 months of observations. Every new galaxy found at these distances adds another piece to a puzzle that refuses to fit together. One researcher admitted that they built these machines not to confirm the paradigm but to break it. They just did not know how it would break. And then Webb found something that made massive galaxies look like a minor problem. In the modern universe, there is a rule. For every 10,000 solar masses of stars in a galaxy, there is roughly one solar mass in the central black hole. This ratio holds everywhere we look. The Milky Way follows it. Nearby galaxies follow it. It is a cosmic law until Webb looked at the early universe. Astronomers found a galaxy from when the cosmos was only 570 million years old. They measured the mass of its stars. Then they measured the black hole at its center. The numbers made no sense. The black hole equaled 10% of all the stellar mass combined. For every 10 solar masses of stars, there was one solar mass of black hole. This galaxy broke the rule by a factor of 1,000. Scientists call it an overmassive black hole. The term barely captures how extreme this is. Imagine if your heart weighed 1/10 as much as your entire body. That is the proportion we are seeing in these early galaxies. The black hole is not just at the center, it dominates the entire system. Webb found dozens of these objects. They appear as little red dots in deep field images. The red color comes from hot gas swirling into the black hole. As matter accelerates toward the event horizon, it heats to millions of degrees and radiates energy. This creates a compact, blazing core that outshines the surrounding stars. The discovery challenges everything astronomers thought they understood about galaxy evolution. In nearby galaxies, the black hole and stars grow together. A bigger galaxy has a bigger black hole, maintaining that 1 to 10,000 ratio. The relationship is so consistent that scientists built entire theories around it. These early galaxies show a completely different pattern. The black holes grew first and grew fast. They became massive before their host galaxies had time to form many stars. One researcher described it as a baby with the heart of a giant. The proportions are all wrong. How did these black holes get so big so quickly? There are two main theories. The first involves stellar collapse. When massive stars die, they can form black holes. These black holes then grow by consuming nearby matter. But this process takes time. Even if a black hole eats constantly at the maximum possible rate, growing from a stellar remnant to millions of solar masses in 500 million years requires nearly perfect conditions. The second theory proposes that some black holes were born big. Instead of forming from collapsing stars, they formed when massive clouds of gas collapsed directly into black holes. These primordial black holes would start with masses of thousands or even millions of solar masses. They bypass the slow stellar formation route entirely. Webb data now supports the direct collapse scenario. Several observations hint that these massive black holes could not have grown from stellar seeds in the time available. They must have started large. This creates its own mystery. What special conditions allow a gas cloud to collapse directly into a black hole instead of forming stars? The story gets stranger still. These overmassive black holes are not randomly scattered across the early universe. The black holes sit in a network. Astronomers mapping the early universe discovered that little red dots cluster together in the cosmic web. This is the large-scale structure of the universe, where galaxies gather along filaments of dark matter like beads on invisible strings. The positioning tells us something critical about when and how these black holes formed. More evolved galaxies appear at the nodes where filaments intersect. Less developed galaxies scatter along the filaments themselves. The little red dots occupy specific locations in this web. They are not the most massive structures, but they are among the most active. Their black holes are consuming matter at ferocious rates. One survey analyzed 7 little red dots from when the universe was 12.5 billion years younger than today. All 7 showed the same pattern: overmassive central black holes in relatively small galaxies. The consistency is striking. This is not a few weird outliers. It appears to be a distinct population of early universe objects. The black holes emit radiation as they feed. This energy pours into the surrounding gas, heating it and pushing it away. Astronomers call this feedback. In nearby galaxies, black hole feedback regulates star formation. Too much feedback and new stars cannot form. Too little and stars form so rapidly that the galaxy runs out of gas. In these early galaxies, the feedback might explain why the galaxies stayed small. The massive black holes turned on early, blasting their surroundings with energy. This prevented the galaxy from forming many stars. The black hole essentially kept its host galaxy stunted. Only later, after the black hole quieted down, could gas cool and form stars at normal rates. This would gradually restore the ratio we see in modern galaxies. But there is a timing problem. If black holes form first and prevent star formation, where did the black holes come from? They need gas to grow. If they are blasting all the gas away with feedback, how did they get massive in the first place? The sequence of events does not quite work. Some researchers propose a burst scenario. The black hole forms and goes through a rapid growth phase, consuming massive amounts of gas before the feedback energy builds up enough to push material away. During this window, the black hole can grow to millions of solar masses. Then the feedback kicks in, shutting down both black hole growth and star formation. Later, the system settles into a calmer state. Others point to mergers. If two galaxies collide, their central black holes can merge. This instantly creates a more massive black hole. Early universe galaxies existed closer together, making mergers more common. A series of mergers could build up supermassive black holes quickly. Webb has already found evidence of merging black holes in the early universe, lending support to this idea. Recent observations add another twist. Some overmassive black holes sit in regions with surprisingly low chemical enrichment. Stars produce heavy elements when they die. These elements enrich the surrounding gas. A galaxy with many stars should show high levels of these elements. But some overmassive black hole hosts show low enrichment, suggesting few stars have lived and died there. This fits the primordial black hole theory. If the black hole formed directly from pristine hydrogen and helium gas, it would not need prior generations of stars. The low chemical enrichment would be expected. But confirming this requires more observations. Each spectrum Webb captures adds detail to the picture. What astronomers know for certain is that the early universe operated differently than the modern one, and the differences go beyond just black holes. 350 years ago, a star exploded. The supernova flash raced outward at the speed of light, crossing the empty space between stars. In 2025, that pulse of radiation reached a cloud of interstellar dust and gas. The James Webb telescope watched what happened next. The light hit the dust and illuminated it from within. Webb captured the glow in exquisite detail. What scientists saw resembled the knots and walls of wood grain. Tightly packed sheets of material revealed structures on scales of 400 astronomical units. That is less than 1/100th of a light year. This is finer detail than anyone knew existed in the interstellar medium. Astronomers call this phenomenon a light echo. It works like an audio echo bouncing off canyon walls, except with light. The supernova flash acts as a cosmic spotlight, briefly illuminating material that would otherwise remain invisible. As the light pulse expands outward, it progressively lights up more distant material, creating an echo that moves through space. The observations targeted a light echo near the Cassiopeia A supernova remnant. This is the shattered remains of a star that exploded in the 1600s. Webb did not look at the remnant itself. Instead, it focused on background material lit up by the ancient explosion. The material has nothing to do with the star that exploded. It is unrelated interstellar dust and gas that happened to be in the right place at the right time. The fine structure shocked the research team. They expected to see diffuse, formless clouds. Instead, they found organized layers. One scientist described it as an onion with nested shells. The sheets of material stack upon one another in intricate patterns. Some appear influenced by magnetic fields threading through space, aligning the dust into parallel formations. This discovery matters because the space between stars is not empty. Every cubic meter contains atoms of gas and grains of dust. Most of this material clumps together in clouds. These clouds give birth to new stars. Understanding their internal structure helps astronomers grasp how star formation works. Before Webb, scientists could only study the outsides of these clouds. Now they can peer inside. The sheet-like structures measure about 400 astronomical units across. For scale, our entire solar system, including the orbit of Neptune, spans only 120 astronomical units. These sheets are several times larger than our planetary system, yet they are just small features within much larger clouds. Why does the material organize into sheets rather than random blobs? Magnetic fields provide one explanation. The interstellar medium is threaded with magnetic field lines. Charged particles and dust grains tend to align along these fields. Over time, this creates elongated structures. Turbulence in the gas also plays a role, stirring the material into complex patterns. The researchers believe that most dense, dusty regions in space look like this on the inside. We have just never been able to look inside them before. Every molecular cloud, every star-forming region, probably contains similar layered structures. Webb has given us a template for understanding the three-dimensional architecture of interstellar space. These observations also reveal how matter moves between stars. The sheets might channel gas flows, guiding material along specific paths. Where sheets intersect or compress, conditions might favor star formation. Understanding this helps predict where new stars will ignite. The light echo technique opens a new way to study the interstellar medium. Astronomers can wait for supernovae or other bright transient events to illuminate different regions of space, then observe the revealed structures with Webb. Each echo provides a snapshot of a different volume of interstellar space. But while Webb was studying the space between stars in our region, it was simultaneously looking at stars dying in the most distant reaches of time. On March 14, 2025, a space telescope detected a flash of gamma rays. The burst lasted several seconds. Within hours, ground-based telescopes around the world swiveled to observe the fading glow. The light revealed something extraordinary. This explosion happened when the universe was only 730 million years old. The burst originated from a massive star at the moment of its death. Stars more than 10 times heavier than our home star live fast and die violently. When their nuclear fuel runs out, the core collapses in less than a second. The outer layers crash inward, rebound off the collapsing core, and explode outward. This is a supernova. In the most massive stars, the collapse also generates jets of material that punch through the star at nearly the speed of light. These jets produce gamma rays, the highest energy form of light. When one of these jets points toward Earth, we detect a gamma ray burst. This is exactly what happened on that March morning. Astronomers had seen distant gamma ray bursts before, but this one set a record. The light had been traveling for more than 13 billion years. We were watching a star explode during the epoch of reionization, when the first stars and galaxies were clearing the fog of neutral hydrogen that filled the early universe. The discovery was not accidental. Ground-based telescopes confirmed the extreme distance using spectroscopy, but the crucial observations came 110 days after the burst, when Webb turned its attention to the region. By then, the initial flash had faded. What remained was the supernova itself, a slower and dimmer event than the gamma-ray burst. Webb separated the fading light of the supernova from the much dimmer glow of its host galaxy. This is technically challenging. The supernova outshines its host by a significant factor, and both appear as a single point of light from Earth. Webb's sharp infrared vision made the separation possible. The telescope identified both the explosion and the galaxy that hosted the dying star. The observations revealed something unexpected. This ancient supernova looked remarkably similar to supernovae in the modern universe. Astronomers compared it to a well-studied nearby supernova from 1998. The brightness, the spectrum, and the evolution over time matched closely. Despite occurring in a vastly different environment, the explosion followed the same basic physics. This is both comforting and puzzling. Comforting because it suggests that the laws of physics have not changed over cosmic time. The way massive stars die today is the same as how they died billions of years ago. Puzzling because the early universe had very different conditions. Stars back then formed from nearly pure hydrogen and helium. Modern stars contain heavier elements created by previous generations of stars. These heavy elements affect how stars live and die. The similarity between ancient and modern supernovae suggests that metallicity, the amount of heavy elements in a star, might matter less than astronomers thought. Or perhaps the most massive stars behave similarly regardless of their composition. More observations of distant supernovae will help resolve this question. The host galaxy itself provides clues about the early universe. It is small and faint, barely detectable even with Webb. This tells us that massive stars were forming and dying in some of the smallest galaxies. These galaxies might have been building blocks that merged to form larger structures over time. Finding supernovae this distant also opens a new way to study the early universe. Each explosion acts as a beacon, illuminating its surroundings for a brief period. Astronomers can study the gas around the dying star, measuring its composition and density. This reveals conditions in the interstellar medium billions of years ago. Gamma-ray bursts paired with supernovae also test models of stellar evolution. Theorists predict how massive stars should behave at different cosmic epochs. Observations either confirm or challenge these predictions. The close match between this ancient supernova and modern ones supports current stellar evolution models, but raises questions about why metal-poor environments do not produce more significant differences. Yet even as this star was exploding in isolation, elsewhere in the early universe, black holes were not dying alone. The galaxy had two bright cores. Astronomers noticed this immediately when they examined Webb images of a system called ZS7. The galaxy existed 740 million years after the Big Bang. At first, scientists wondered if they were seeing a single galaxy with unusual structure. Then they analyzed the spectrum. The data showed fast-moving gas near both bright points. The gas moved at velocities of hundreds of kilometers per second, swirling in tight orbits. This is the signature of matter falling into a black hole. The gas heats up as it accelerates, reaching millions of degrees. It emits characteristic wavelengths of light that reveal the presence of an actively feeding black hole. Both cores showed this signature. ZS7 contained two supermassive black holes orbiting each other. This is the earliest black hole merger ever detected. The two objects are spiraling inward, destined to collide and combine into a single, more massive black hole. Webb's sharp imaging allowed the team to spatially separate the two black holes. They are close together but distinct. Ground-based telescopes would see them as a single blurred point. Space-based telescopes, before Webb, lacked the infrared sensitivity to study such distant objects in detail. Only Webb could resolve this system and identify it as a merger in progress. The discovery has profound implications for understanding how supermassive black holes grow. In the local universe, most large galaxies contain a central supermassive black hole. But how did these objects grow to millions or billions of solar masses? One mechanism is merging. When two galaxies collide, their central black holes eventually sink to the center of the merged system and combine. If mergers were rare in the early universe, black holes would have to grow primarily by consuming gas. This is a slow process. Even eating at the maximum possible rate, a stellar mass black hole takes hundreds of millions of years to reach supermassive scales. Finding mergers at cosmic dawn suggests they happen frequently enough to accelerate black hole growth significantly. The two black holes in ZS7 are not yet touching. They orbit each other, gradually losing energy and spiraling closer. This energy loss happens through gravitational waves, ripples in space-time predicted by Einstein. As the black holes circle each other, they emit these waves, carrying away orbital energy. This causes the orbit to shrink. When the black holes finally merge, the collision will release a tremendous burst of gravitational waves. Future gravitational wave detectors will be able to detect mergers like this one. Current detectors on Earth are sensitive to smaller black holes merging in the nearby universe. The next generation of space-based detectors will extend the reach to supermassive black holes at high redshift. Detecting gravitational waves from early universe black hole mergers will reveal the rate at which these events occurred. Astronomers can then calculate how much of the black hole mass growth came from mergers versus gas accretion. This will constrain models of black hole formation and evolution in the first billion years after the Big Bang. The ZS7 system also tells us about galaxy mergers in the early universe. When galaxies collide, their stars, gas, and dark matter interact. Stars rarely collide directly because space between them is vast. But gas clouds crash together, triggering bursts of star formation. The collision compresses the gas, making it dense enough to form new stars. Eventually, the two galaxies merge completely, forming a single, more massive galaxy. The central black holes take longer to merge because they must lose angular momentum to reach the center. Gas and stars carry away this momentum through gravitational interactions. The black holes spiral inward over millions of years before finally coalescing. The stellar mass of ZS7 resembles the Large Magellanic Cloud, a small galaxy orbiting the Milky Way. Imagine if the Large Magellanic Cloud contained two supermassive black holes as large as the one in the Milky Way center. The black holes would dominate the dynamics of the entire galaxy. This is what we see in ZS7. Finding this merger so early in cosmic history suggests that the processes shaping galaxies and black holes today were already operating back then. But something else about these early systems continued to baffle scientists. Light from the most distant galaxies has been traveling for so long that the universe has expanded significantly during the journey. This expansion stretches the light. Astronomers measure this stretching using redshift, a number that indicates how much the wavelength has increased. A redshift of 1 means wavelengths have doubled. A redshift of 2 means they have tripled. Jades has a redshift of 14.32. The light from this galaxy has been stretched by a factor of 15. Ultraviolet light that left the galaxy has arrived at Webb as infrared. This is why infrared telescopes are essential for studying the early universe. The light has shifted so far toward the red end of the spectrum that visible light telescopes cannot see it. Measuring redshift requires spectroscopy. Webb splits incoming light into its component wavelengths, creating a spectrum. Certain elements in the galaxy produce emission or absorption lines at specific wavelengths. Scientists know what these wavelengths should be when the light is emitted. By measuring where the lines appear in the observed spectrum, they can calculate how much the light has been stretched. For jades, hydrogen emission lines that should appear in the ultraviolet are observed in the infrared. The shift is so large that there is no ambiguity. This galaxy is genuinely ancient. The light we see left the galaxy 290 million years after the Big Bang. Since then, it has been traveling through expanding space for more than 13 billion years. The expansion of the universe also affects how we perceive distance. When astronomers say a galaxy is 13.5 billion light-years away, they are describing the light travel distance. But space has been expanding during those 13.5 billion years. If you could freeze the expansion right now and measure the distance to that galaxy, it would be farther than 13.5 billion light-years. Much farther. This co-moving distance accounts for the expansion that has occurred since the light began its journey. Redshift offers a more fundamental measurement than distance. It directly tells us how much the universe has expanded since the light was emitted. A redshift of 14 means the universe has grown by a factor of 15 since that light left its source. The wavelength of every photon has stretched by the same factor. This stretching affects more than just color. It also dims the light. Photons arrive at Earth with less energy than they had when emitted. Each photon is redshifted to a longer wavelength and lower energy. Additionally, photons arrive more slowly because the path they travel through space has expanded. Both effects combine to make distant objects appear much fainter than they would be at close range. Webb compensates for this dimming. With its enormous mirror and sensitive detectors, the mirror collects as much light as possible. The detectors are cooled to a few degrees above absolute zero, reducing noise and allowing them to detect extremely faint signals. Even so, observing the most distant galaxies requires hours of exposure time. The JADE's deep field observations totaled more than 70 hours of telescope time. This is an enormous investment for a facility where every hour is precious. Astronomers must justify such long observations by showing that the science return is worth the cost. Discovering the most distant known galaxy certainly qualifies. The redshift record keeps advancing. Before JADES, the most distant known galaxy had a redshift of 13.2. JADES pushed the record to 14.32. More distant galaxies likely exist, waiting to be discovered. Webb can detect galaxies with redshifts up to 20 if they are bright enough. This corresponds to galaxies forming in the first 200 million years after the Big Bang. Finding such galaxies is difficult. They are rare and extremely faint. Astronomers must observe large areas of sky with very long exposure times. Then they must painstakingly analyze the data, identifying candidates and following up with spectroscopy to confirm distances. Each new record holder represents months or years of work. But the effort reveals fundamental truths about cosmic dawn. The first galaxies were not hiding in the distant darkness. They were bright, active, and surprisingly mature. And the universe they inhabited was expanding in a way that still confuses scientists today. Astronomers measure the expansion rate of the universe using a number called the Hubble constant. It tells you how fast galaxies are moving away from each other per unit of distance. The current value is around 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, a galaxy recedes 70 kilometers per second faster. A megaparsec equals about 3.3 million light-years. So, a galaxy 3.3 million light-years away recedes at 70 kilometers per second. A galaxy 6.6 million light-years away recedes at 140 kilometers per second. The pattern continues linearly with distance. There are two main ways to measure the Hubble constant. The first uses light from the cosmic microwave background. This is radiation left over from the Big Bang itself, now stretched into microwave wavelengths. The pattern of fluctuations in this radiation tells us the composition and geometry of the early universe. From this, cosmologists can calculate how fast the universe should be expanding today. They get a value of 67.4 kilometers per second per megaparsec. The second method uses nearby galaxies with supernovae. Certain types of stellar explosions have predictable brightness. By measuring how bright they appear, astronomers can calculate their distance. Combining distance measurements with velocity measurements gives the Hubble constant directly. This method yields a value of around 73 kilometers per second per megaparsec. These two values do not agree. The difference is small in absolute terms, but large enough to be highly significant. It persists despite decades of refinement to both methods. This disagreement is the Hubble tension. When Webb began operations, some scientists hoped it would resolve the tension. Perhaps one method contained a subtle error that better observations would reveal. Webb has now collected the largest dataset yet on nearby supernovae. The result confirms the Hubble Space Telescope measurements. The local universe is expanding at 73 kilometers per second per megaparsec. The tension is real. What could explain this discrepancy? One possibility is that our understanding of the early universe is incomplete. The cosmic microwave background measurements assume a specific cosmological model. If that model is wrong, the predicted expansion rate would also be wrong. Perhaps dark energy behaves differently than assumed. Perhaps there is an unknown component of the universe affecting the expansion. Another possibility involves the local universe. Maybe the region of space we inhabit is somehow unusual, expanding faster than the average. We might live in a cosmic void, a large underdense region where the expansion rate differs from the global average. But measurements of our local environment suggest we are in a fairly typical region. A third possibility is that the universe changed its behavior over time. The cosmic microwave background shows us the universe as it was 380,000 years after the Big Bang. Supernova measurements show us the universe over the last few billion years. If something happened in between to accelerate the expansion, it would explain the discrepancy. Some theorists propose new physics. Perhaps gravity behaves differently on cosmological scales than we think. Perhaps dark energy is not constant, but has been growing stronger over time. These ideas require modifying general relativity, Einstein's theory of gravity. Scientists are reluctant to take such a step without compelling evidence. Recent observations with Webb have eliminated one possible explanation. Some researchers suggested that the Hubble Space Telescope measurements were systematically biased by an instrumental error. Webb uses completely different instruments and observing techniques. The fact that it gets the same answer as Hubble rules out instrumental bias as the cause of the tension, this leaves us with a genuine mystery. Two rigorous methods, both refined over decades, give different answers for how fast the universe is expanding. One of them must be wrong, or something about the universe is more complicated than current models allow. Either way, resolving the tension will likely require new physics, and the mysteries extend beyond just the expansion rate. The first stars in the universe were different from anything that exists today. They formed from pristine gas, untouched by previous generations of stars. Just hydrogen, helium, and trace amounts of lithium created in the Big Bang. No carbon, no oxygen, no iron, nothing heavier than lithium. Astronomers call these population 3 stars. They have never been directly observed. Every star we have studied contains at least some heavy elements. But theory demands that population 3 stars must have existed. Someone had to make the first heavy elements. Those elements came from the first generation of stars. These primordial stars would have been massive. Without heavy elements to help cool the gas, star-forming clouds remained hot. Hot gas resists gravitational collapse. Only the most massive clouds could overcome this resistance and form stars. Simulations suggest population 3 stars typically weighed 50 to 500 times more than our home star. Massive stars burn bright and die young. A star 100 times heavier than our star exhausts its fuel in just a few million years. It then explodes as a supernova, scattering its chemically enriched material into space. The next generation of stars forms from this enriched gas, containing the heavy elements forged in the first stars. Population 3 stars should have disappeared billions of years ago. They lived too briefly to survive to the present day, but we might still see them if we look far enough back in time. Webb can observe galaxies from when the universe was less than 500 million years old. This is early enough that some population 3 stars might still be shining. Finding them is extraordinarily difficult. A single massive star is too faint to see across billions of light years. Astronomers must look for the signature of many population 3 stars together. The spectrum of pure hydrogen and helium stars differs from metal-enriched stars. Certain emission lines should be strong, others weak or absent. Webb observations of a galaxy called GNZ 11 show tantalizing hints. This galaxy existed 430 million years after the Big Bang. Spectra from the outer regions show strong hydrogen emission with peculiar ratios between different lines. The pattern matches what theorists predict for regions where population 3 stars are forming. The evidence is not definitive. Other processes could produce similar spectral features, but the possibility excites astronomers. If confirmed, this would be the first detection of the stars that brought light to the universe. These objects seeded the cosmos with the first heavy elements, making planets and eventually life possible. Population 3 stars also influenced the reionization of the universe. After the Big Bang, the universe was hot and ionized. As it expanded and cooled, electrons and protons combined to form neutral hydrogen atoms. The universe became transparent but dark, filled with neutral gas that absorbed most wavelengths of light. This is called the cosmic dark ages. When the first stars ignited, their ultraviolet radiation ionized the hydrogen around them, creating bubbles of ionized gas. As more stars formed, these bubbles grew and merged. Eventually, the entire universe became ionized again. This epoch of reionization represents one of the major phase transitions in cosmic history. Population 3 stars likely played a crucial role in reionization. Their intense ultraviolet output would have ionized large volumes of space. Early galaxies packed with these stars would have been reionization powerhouses, clearing the neutral fog and allowing light to travel freely through space. Webb is hunting for these objects systematically. Large survey programs are imaging and obtaining spectra of hundreds of early galaxies. Each spectrum might contain the telltale signs of population 3 stars. Even if only a small fraction of early galaxies still host these primordial stars, the surveys should find them. The discovery would connect us directly to the first chapter of cosmic history. We would see the ancestors of all stars, the original engines that transformed the universe from darkness to light. But while scientists search for the first stars, they have stumbled upon objects they cannot explain at all. They appear as tiny crimson points in Webb's deep field images, compact, bright, red. Astronomers call them little red dots, a deliberately vague name for objects that defy classification. They exist in the early universe at redshifts between 5 and 8. That corresponds to when the cosmos was between 1 and 2 billion years old. The red color comes from hot gas around a central black hole. As matter spirals inward, friction heats it to millions of degrees. This creates an accretion disk that glows across the electromagnetic spectrum. The specific color we see depends on the temperature of the gas and how much dust surrounds the system. Heavy dust obscures shorter wavelengths, making the object appear red. Little red dots are not rare. Large surveys have found dozens of them. They make up several percent of the galaxy population at these early epochs. This abundance surprises scientists. Nobody predicted that so many compact red objects would exist in the early universe. What makes them confusing is their spectrum. When astronomers split the light into wavelengths, the pattern shows both broad emission lines characteristic of black holes and narrower features associated with star formation. The broad lines indicate gas moving at thousands of kilometers per second near a black hole. The narrow lines indicate gas moving much more slowly in star-forming regions. Normally, these two signatures come from different types of objects. Active galactic nuclei, powered by supermassive black holes, show broad emission lines. Star-forming galaxies show narrow lines. Little red dots show both simultaneously. Are they galaxies with unusually active black holes? Or black holes with unusually strong star formation around them? Or something else entirely? The compact size adds to the mystery. These objects appear point-like even to Webb. Their emission comes from a region smaller than about 1,000 light-years across. For comparison, the Milky Way spans 100,000 light-years. Little red dots pack tremendous energy output into a volume 100 times smaller than a typical galaxy. Some researchers argue that little red dots are just heavily dust-obscured quasars. Quasars are the most luminous objects in the universe, powered by matter falling into supermassive black holes. If you surround a quasar with enough dust, the visible and ultraviolet light gets absorbed and re-radiated as infrared. This makes the object appear red and compact. Others suggest that little red dots represent a brief transitional phase in galaxy evolution. Perhaps they are galaxies in the process of forming their first supermassive black hole. The black hole has just turned on and is rapidly consuming gas. This creates the active nucleus signature. Meanwhile, the host galaxy continues forming stars, producing the narrow emission lines. Eventually, the black hole grows large enough that its feedback energy suppresses star formation, and the object evolves into a typical quasar. A third possibility involves the environment. Little red dots cluster together in the cosmic web, sitting at specific locations in the large-scale structure. Perhaps their formation requires special conditions found only in these dense regions. Collisions between gas clouds or interactions between multiple small galaxies might trigger both black hole growth and star formation simultaneously. Webb observations are testing these ideas. By obtaining detailed spectra of many little red dots, astronomers can measure properties like the black hole mass, the star formation rate, the amount of dust, and the chemical composition. These measurements distinguish between different formation scenarios. One recent analysis examined 7 little red dots from the same cosmic epoch. All 7 showed signs of overmassive black holes, with black hole mass equaling around 10% of the stellar mass. This consistency suggests we are seeing a real population with shared characteristics, not just random oddballs. The existence of so many little red dots also constrains models of black hole formation. If these objects are common in the early universe, then the processes creating them must be robust and efficient. This might favor scenarios where black holes form rapidly through direct collapse or accelerated accretion. Another puzzle involves the host galaxies themselves. When Webb images the regions around little red dots with extreme sensitivity, it sometimes detects faint extended emission. This shows that the compact red core sits within a larger, dimmer galaxy. The galaxy is so faint compared to the active nucleus that it almost disappears. Understanding the relationship between the dim galaxy and the brilliant core will reveal how black holes and their hosts co-evolve. Little red dots represent one of the biggest surprises from Webb's first few years. Nobody anticipated finding so many of these enigmatic objects. Each new observation adds pieces to the puzzle, but the complete picture remains elusive. And while little red dots confuse scientists on small scales, the large-scale structure of the universe presents its own challenges. The universe is not uniform. Matter clumps together under gravity, forming a vast network called the cosmic web. Galaxies gather along filaments of dark matter, creating chains of light stretching across hundreds of millions of light years. Where filaments intersect, massive galaxy clusters form. Between the filaments lie voids, vast, underdense regions containing few galaxies. This structure emerged from tiny fluctuations in density present just after the Big Bang. Regions slightly denser than average attracted more matter through gravity. Over billions of years, these small variations grew into the web we see today. Tracing the web back in time reveals how structure in the universe evolved from smooth beginnings to the lumpy distribution we observe. Webb sees this structure at unprecedented distances. By mapping galaxies in the early universe, astronomers can reconstruct what the cosmic web looked like when reality was less than 2 billion years old. The web already existed back then, though in a less developed form. Filaments were shorter and less defined. Clusters were just beginning to form. One recent survey examined a specific patch of sky in extreme detail. The team identified thousands of galaxies at various distances. By measuring their redshifts, astronomers placed each galaxy at its correct position in three-dimensional space. This created a map showing how galaxies distributed themselves at different cosmic epochs. The map reveals that the cosmic web has been in place for most of cosmic history. Even at redshift 8, when the universe was less than 1 billion years old, galaxies clearly cluster along filaments. The basic architecture was already established. What changed over time was the thickness of the filaments and the mass of the clusters at the nodes. Understanding this evolution helps constrain cosmological models. The rate at which structure grows depends on the amount and properties of dark matter and dark energy. Too little dark matter and structure forms too slowly. Too much, and it forms too quickly. The observed evolution of the cosmic web provides a crucial test. Dark matter makes up about 85% of all matter in the universe. It does not emit, absorb, or reflect light. We detect it only through its gravitational effects. Dark matter forms the skeleton of the cosmic web. Galaxies form where dark matter is densest, tracing the underlying dark matter distribution. Webb cannot see dark matter directly, but by mapping visible galaxies, it maps the dark matter indirectly. Galaxies are biased tracers of the dark matter distribution. They preferentially form in the most massive dark matter halos. By studying how galaxies cluster, astronomers learn about the dark matter structure that shaped their formation. Simulations predict the detailed structure of the cosmic web based on our understanding of dark matter and gravity. These simulations start with initial conditions matching the early universe and evolve forward in time. The results can be compared directly to observations. When simulations match observations, it confirms our models. When they disagree, it suggests missing physics. Recent comparisons between Webb observations and simulations show good agreement on large scales. The overall distribution of galaxies matches predictions. But on smaller scales, discrepancies appear. Simulations predict more small galaxies than observed in some regions and fewer in others. This might indicate that galaxy formation is more complex than current models allow. The cosmic web also affects galaxy properties. Galaxies in dense regions evolve differently than galaxies in underdense regions. Dense environments have more frequent galaxy interactions and mergers. These collisions trigger star formation and funnel gas into central black holes. Galaxies in voids experience fewer interactions and evolve more quietly. Webb observations show that little red dots preferentially occupy specific locations in the cosmic web. They are not found everywhere, but cluster in moderately dense regions along filaments. This environmental dependence provides clues about what triggers their formation. Perhaps the combination of sufficient gas supply and frequent interactions creates the conditions for rapid black hole growth. Mapping the cosmic web at different epochs also tracks how matter flows through the universe. Gas streams along filaments toward galaxy clusters, feeding star formation in galaxies along the way. When gas reaches a cluster, it can be heated to high temperatures by shocks and turbulence, shutting down star formation. Webb can observe these processes in action by studying galaxies at different positions in the web. The large-scale structure connects the smallest and largest scales in the universe. The properties of individual galaxies depend on their location in the web. The evolution of the web depends on the cosmological parameters governing the universe as a whole. By studying structure formation, astronomers probe fundamental physics. Yet, even as the web itself takes recognizable form early on, the galaxies within it behave strangely. In the nearby universe, galaxies have a typical density. If you count the total mass of stars and divide by the volume the galaxy occupies, you get a number. For most galaxies, that number falls within a certain range. Early universe galaxies break this pattern completely. Measurements show that high redshift galaxies are much denser than local galaxies. Some are 1,000 times denser. This means they pack the same mass of stars into a volume 1,000 times smaller. The stars in these galaxies orbit in tight, crowded regions where stellar encounters might be common. This creates a paradox. If galaxies start small and dense, then grow large and diffuse, something must puff them up over time. Galaxies need to expand without gaining much mass. This is the opposite of what most theories predicted. Simulations generally show galaxies gaining mass through mergers and star formation, not inflating like balloons. One explanation involves mergers. When two galaxies collide, their stars do not actually collide. Stars are so small and far apart that they pass through each other during a galactic merger. But the gravitational interactions redistribute the stars. The merged galaxy ends up larger and less dense than either parent galaxy. Repeated mergers over billions of years could gradually decrease the average galaxy density. Another factor is the dark matter halo. Every galaxy sits at the center of a massive dark matter halo that extends far beyond the visible stars. As the halo grows through mergers and accretion, the distribution of dark matter changes. This alters the gravitational potential, which can cause stars to migrate outward. The galaxy expands to fill a larger volume even if no new stars form. Feedback from supernovae and black holes also plays a role. Energetic winds driven by exploding stars or active galactic nuclei can push gas out of the galaxy. This removes mass from the central regions, decreasing the gravitational pull. Stars then move to larger orbits, decreasing the overall density. This process, called galaxy-scale winds, is observed in many systems. Some researchers question whether the high densities are real. They point out that measuring the size of a distant galaxy is difficult. The galaxy appears as a small smudge in images. Determining where the galaxy ends and the background begins involves assumptions about the galaxy's light profile. Different assumptions give different sizes. Webb's superior resolution helps address this concern. It can resolve features in distant galaxies that Hubble could not. Measurements with Webb confirm that early galaxies are indeed more compact than expected. The effect is real, though the exact density difference depends on how you define the galaxy boundary. The density evolution also connects to the star formation history. If galaxies form most of their stars early and then stop, they will grow primarily through mergers without forming many new stars. This would maintain their mass while increasing their size, decreasing density. Webb observations show that many early galaxies have high star formation rates, so this scenario does not apply universally. Another consideration involves the role of gas. Galaxies in the early universe contain a higher fraction of gas relative to stars compared to local galaxies. Gas is more compressible than stars. A gas-rich galaxy can be denser because the gas occupies less volume. As the galaxy ages and converts gas into stars, the stellar component dominates. Stars, once formed, do not compress further. This naturally leads to a decrease in overall density. The observed density evolution provides a test for cosmological models. If the universe expands according to a certain metric, galaxies should evolve in a predictable way. If observations disagree with predictions, it suggests either the metric is wrong or galaxy evolution involves processes not included in current models. Some alternative cosmological models predict that distant galaxies should have similar sizes to local galaxies. In these models, the universe does not expand or expands in a different way. Redshift comes from motion through space rather than the expansion of space itself. These models are controversial and not accepted by mainstream astronomy, but the density measurements provide data that any model must explain. Whatever the explanation, Webb has revealed that galaxies in the early universe do not simply look like smaller versions of modern galaxies. They are fundamentally different in their structure and dynamics. Understanding this transformation is key to understanding how galaxies form and evolve, and the differences extend beyond just density. Jade's should be dim. It sits more than 13 billion light-years away. Light from the galaxy has traveled across expanding space for most of cosmic history. By the time it reaches Webb, each photon has been redshifted, losing energy. The photon flux has also been diluted by the expansion. Distant objects always appear fainter than nearby ones. Yet Jade's is bright, surprisingly bright. So bright that Webb could have detected it even if it were 10 times fainter. This raises an obvious question. If this bright galaxy is easy to find, where are all the other bright galaxies at similar distances? They should be everywhere. The answer is that they are everywhere. Webb has found numerous bright galaxies at high redshift, far more than predicted by pre-launch models. These galaxies dominate the early universe in a way that cosmologists did not anticipate. The universe at cosmic dawn was not dim and quiet. It was ablaze with star formation. Measuring a galaxy's brightness tells you about its star formation rate. Bright galaxies form stars rapidly. The ultraviolet light from young, hot stars makes the galaxy luminous. By measuring how bright a galaxy appears and correcting for distance and redshift, astronomers can estimate how many stars form per year. Jade's forms stars at a prodigious rate. Estimates suggest dozens of solar masses of new stars per year. For comparison, the Milky Way currently forms about 1 or 2 solar masses of stars per year. Jade's is tens of times more active, despite being much smaller. This high star formation rate concentrated in a small volume creates the observed brightness. The galaxy's size adds to the puzzle. At over 1,600 light-years in diameter, it is larger than expected for its age. Simulations predicted that galaxies at this epoch would be tiny, perhaps a few hundred light-years across. Jade's is several times larger. It has had time to build substantial structure. What makes a galaxy bright is ultimately the number of young, massive stars it contains. These stars burn fiercely, emitting copious ultraviolet light. A galaxy with more young stars is brighter, so the brightness mystery reduces to a question about star formation. Why do early galaxies form stars so efficiently? One factor is gas supply. Galaxies in the early universe are gas-rich. They have not yet converted much of their gas into stars. With abundant fuel, star formation can proceed rapidly. The gas is also pristine, composed mostly of hydrogen and helium. It flows into the galaxy along cosmic Webb filaments, providing a steady supply. Another factor is the lack of heavy elements. In the modern universe, Dust grains formed from heavy elements help cool gas clouds, facilitating star formation. But dust also absorbs ultraviolet light, dimming galaxies. Early universe galaxies have little dust, so their starlight escapes more easily. They appear brighter than a comparable nearby galaxy with more dust. Feedback mechanisms also differ in the early universe. In nearby galaxies, supernovae and black hole winds regulate star formation. They heat or expel gas, preventing it from collapsing to form new stars. Early galaxies might have weaker feedback because their black holes are still growing and supernovae are just beginning to enrich the interstellar medium. Weaker feedback allows star formation to proceed at higher rates. However, these explanations only partially resolve the brightness puzzle. Even accounting for high gas content and weak feedback, simulations struggle to produce galaxies as bright as observed. There is a gap between theory and observation. Either the simulations are missing key physics, or the observations require reinterpretation. Some researchers propose that the luminosity is temporarily boosted by a starburst phase. During a galaxy merger, or after a large influx of gas, star formation can surge to rates far above the average. These bursts last only a few tens of millions of years, but during that time the galaxy appears exceptionally bright. If we happen to observe galaxies during these brief, bright phases, they would appear more luminous than expected based on their long-term average star formation rate. Another possibility involves the stellar initial mass function, the distribution of stellar masses when stars form. In the local universe, most star formation produces low-mass stars, with fewer high-mass stars. If the early universe preferentially produced more high-mass stars, the total ultraviolet luminosity per unit mass of stars formed would be higher. This would make early galaxies appear brighter without requiring more total star formation. Testing these ideas requires detailed observations of many galaxies. Webb is conducting large surveys to build up statistics. By examining hundreds of early galaxies, astronomers can determine whether the bright objects are rare outliers or represent a typical population. Current data suggests they are typical. The early universe was genuinely brighter than models predicted. This has implications for reionization. Bright galaxies produce more ionizing photons. If the early universe contained more bright galaxies than expected, it produced more ionizing radiation. This could have reionized the universe faster than previous models suggested. Webb observations of reionization-era galaxies will test this idea. Meanwhile, on smaller scales, Webb found something extraordinary. Alpha Centauri is our closest stellar neighbor. 3 stars orbit each other just over 4 light-years from Earth. 2 of them, Alpha Centauri, A and B, resemble our home star. The third, Proxima Centauri, is a small red dwarf. This system has fascinated astronomers for decades. If there are planets around our nearest neighbors, we want to find them. Proxima Centauri hosts at least 2 confirmed planets. One orbits in the habitable zone, where liquid water could exist on a rocky surface. But Alpha Centauri, A and B, have been harder to search. They are bright stars, and their glare overwhelms the faint signals from any planets. Ground-based telescopes struggle to detect planets around such brilliant nearby stars. Webb changed the game. Using its mid-infrared instrument, astronomers devised a custom observing strategy to peer into the glare of Alpha Centauri A. They found something. A faint infrared source sits about twice Earth's distance from the star. The signal is consistent with a large planet, possibly a gas giant. This detection is tentative. Confirming it requires additional observations to rule out other explanations. The signal might come from background objects or instrumental artifacts. But if real, it represents our closest planetary neighbor outside the solar system, aside from Proxima's small worlds. Finding a planet at Alpha Centauri would be monumental. The star system is so close that future missions could potentially visit it. Detailed studies of any planets there would provide insights into planet formation and habitability in systems similar to ours. Even a cold gas giant would be valuable for understanding planetary system architecture. The observing technique developed for this detection demonstrates Webb's versatility. The telescope was designed to study the most distant galaxies, not bright nearby stars. Yet, with clever strategies, astronomers can use it for both. This expands Webb's scientific reach and ensures that surprising discoveries come from unexpected places. Alpha Centauri A is slightly larger and brighter than our home star. If a gas giant orbits there, it likely formed through core accretion, the same process that built Jupiter and Saturn. A solid core accumulates from colliding planetesimals, growing until its gravity becomes strong enough to pull in gas from the surrounding disk. This process requires millions of years and a disk with sufficient material. The potential planet orbits in the habitable zone, the region where temperatures allow liquid water. However, as a gas giant, it would not have a solid surface. But gas giants can have rocky moons. If this planet exists and hosts large moons, those moons might be habitable. This scenario mirrors Jupiter and Saturn's moon systems, where moons like Europa and Enceladus harbor subsurface oceans. Detecting the moons would require even more advanced telescopes than Webb. The moons would be incredibly faint, lost in the glare of both the star and the planet. Future missions dedicated to directly imaging exoplanets might have the capability. These missions would use star shades or coronagraphs to block the star's light, revealing the planets and potentially their moons. The Alpha Centauri system also serves as a test case for theories of planet formation. Our home star formed with certain properties, and the solar system has a specific architecture. By studying planets around similar stars, astronomers can determine which aspects of the solar system are typical and which are unusual. This context helps answer whether systems like ours are common or rare. If future observations confirm the planet, it will become a prime target for follow-up studies. Astronomers will measure its orbit precisely, determine its mass, and search for additional planets in the system. They will also look for signs of a debris disk, leftover material from planet formation that might still orbit the star. Webb's discovery potential extends far beyond distant galaxies. It is revealing the cosmos at all scales, from the most ancient structures to the planetary systems next door. Yet, even as it finds new worlds, it has also uncovered fine details in the space between stars. The space between stars contains more than just emptiness. Gas and dust fill the void, though at extremely low densities. In some regions, the material clumps together into molecular clouds, dense enough to collapse and form new stars. Between these clouds, thinner gas spreads throughout the galaxy. Webb's observations of the Cassiopeia light echo revealed that this interstellar material has intricate internal structure. Scientists measured features as small as 400 astronomical units across. These structures appear as tightly packed sheets, stacked like layers. The discovery changes our understanding of the interstellar medium's organization. Before Webb, astronomers viewed interstellar clouds as relatively smooth and featureless. They knew turbulence stirred the gas, creating some structure, but the details remained hidden. Webb's infrared vision combined with the light echo technique illuminated these structures for the first time. The sheets are real and ubiquitous. Magnetic fields likely sculpt the sheets. The interstellar medium is ionized in many regions, meaning atoms have lost electrons. Charged particles feel magnetic forces. As the gas moves, it drags magnetic field lines along. Over time, this interaction organizes the material into elongated structures aligned with the field. Turbulence also plays a role. Gas in the interstellar medium does not sit still. Supernova explosions, stellar winds, and gravitational instabilities all inject energy, creating chaotic motions. Turbulence naturally generates structure across a wide range of scales, from the size of entire clouds down to the smallest eddies. The sheet-like structures might channel gas flows. Stars form when gas collapses under gravity. If sheets direct, how gas moves. They could influence where stars form. Regions where sheets intersect or compress might become preferential sites for star formation. Understanding these structures helps predict the future evolution of the galaxy. The observations also constrain theoretical models of turbulence in magnetized plasmas. Simulations predict how turbulent energy cascades from large scales to small scales. The observed structure size and orientation provide benchmarks for testing these simulations. When models match observations, it validates our understanding of the physics involved. Webb's ability to probe such fine structure demonstrates the power of infrared astronomy. Visible light is scattered and absorbed by dust, making dense regions opaque. Infrared light penetrates the dust, revealing what lies within. By observing at wavelengths where dust is transparent, Webb sees structures that visible light telescopes cannot. The light echo technique will be applied to other regions. Each supernova or bright transient event illuminates a different volume of interstellar space. By observing multiple light echoes, astronomers can map the three-dimensional structure of the interstellar medium across the galaxy. This creates a comprehensive picture of how matter distributes itself between stars. Knowing the structure matters for understanding star formation efficiency. If gas is organized into dense sheets, the collapse process might proceed differently than in smooth clouds. Sheets might fragment into filaments, which then break up into individual star-forming cores. The hierarchy of structures determines how many stars form and what masses they have. And just as Webb reveals hidden structures in nearby space, it continues discovering new methods to understand the cosmos. Measuring cosmic distances is one of astronomy's greatest challenges. For nearby stars, parallax works. Observe a star from opposite sides of Earth's orbit, and the star appears to shift position slightly against the background. The amount of shift reveals the distance. But this method fails for distant objects. The shifts become too small to measure. For more distant objects, astronomers use standard candles. These are objects with known intrinsic brightness. By measuring how bright they appear, you can calculate their distance. Cepheid variable stars serve as standard candles for nearby galaxies. These pulsating stars have a relationship between their pulsation period and luminosity. Measure the period, and you know the true brightness. Supernovae provide another standard candle for even greater distances. Type Ia supernovae have remarkably consistent peak brightness. They occur when a white dwarf star accumulates matter from a companion until it reaches a critical mass and explodes. The explosion releases a predictable amount of energy, making the supernova a reliable distance indicator. Webb has validated another technique using stars on the tip of the red giant branch. Low-mass stars swell into red giants late in their lives. As they ascend the red giant branch, their brightness increases. Eventually, they reach a maximum brightness and go no brighter. This maximum is called the tip of the red giant branch, and it occurs at a consistent luminosity. By identifying red giant branch stars in a distant galaxy and finding the brightest ones, astronomers can determine how far away the galaxy is. Webb's infrared sensitivity makes it ideal for this technique. Red giants emit strongly in the infrared, and Webb can detect individual stars in galaxies tens of millions of light-years away. A newer method uses carbon stars. These are evolved stars whose atmospheres are enriched in carbon. Carbon stars have consistent colors and brightnesses in the near-infrared spectrum. They serve as another type of standard candle. Webb observations have applied this method to measure distances to nearby galaxies. Using three independent methods together provides a powerful cross-check. If all three methods give the same answer for a galaxy's distance, you can be confident the measurement is accurate. A recent study used Cepheids, red giant branch stars, and carbon stars to measure distances to 10 galaxies. All three methods agreed, yielding a Hubble constant of 70 kilometers per second per megaparsec. This value falls between the two conflicting measurements that created the Hubble tension. It is lower than the value from supernovae, but higher than the value from the cosmic microwave background. This suggests the tension might be less severe than previously thought, or that the situation is more complex. The agreement between multiple methods also validates Webb's measurements. Some skeptics wondered if Webb might have systematic errors affecting distance estimates. By showing that three completely different techniques give consistent answers, the study demonstrates Webb's reliability. The telescope is measuring distances accurately. Refining the Hubble constant matters because it is a fundamental parameter describing the universe. It tells us the universe's age, size, and fate. An accurate value constrains cosmological models and helps predict future evolution. Every improvement in precision narrows the range of possible models. The carbon star method is relatively new. As astronomers gain more experience with it, they will refine the calibration and reduce uncertainties. Future Webb observations will measure distances to more galaxies, further improving the Hubble constant measurement. Combined with measurements at other wavelengths and with other techniques, a consistent picture should eventually emerge. But distance measurements are just one tool for understanding the universe. Webb continues to reveal how cosmic structures form and evolve over billions of years. The black hole does not just pull matter inward, it also blasts energy outward. As gas spirals into the event horizon, friction heats it to millions of degrees. This superheated material radiates intense energy across the electromagnetic spectrum. The pressure from this radiation pushes against surrounding gas, creating powerful winds that flow away from the black hole at thousands of kilometers per second. These winds reshape entire galaxies. When a supermassive black hole feeds actively, the outflowing winds can sweep through the host galaxy, pushing gas out of star-forming regions. Without gas, new stars cannot form. The galaxy's star formation shuts down. This process, called feedback, is one of the most important mechanisms governing galaxy evolution. Webb observations reveal feedback in action in the early universe. Galaxies with overmassive black holes show signs of powerful outflows. Spectra display emission lines with distinct shapes indicating gas moving away from the galaxy center at extreme velocities. The fastest outflows reach 3,000 kilometers per second, fast enough to escape the galaxy's gravitational pull entirely. This explains why early galaxies with massive black holes remain small. The black hole turns on first, consuming gas and growing rapidly. As it feeds, it generates tremendous energy output. This energy drives winds that prevent the surrounding galaxy from forming many stars. The black hole essentially stunts its host galaxy's growth. Eventually, the black hole exhausts the available gas supply. The accretion rate drops, and the energy output decreases. The winds weaken. Gas can now cool and collapse to form stars. The galaxy enters a period of rapid star formation, building up its stellar mass. Over hundreds of millions of years, the galaxy grows until the black hole to stellar mass ratio approaches the values we see in the local universe. This sequence explains the overmassive black holes Webb discovered. We are catching these systems during the first phase, when the black hole has grown large but the galaxy has not yet had time to catch up. Given another billion years, these galaxies would look more normal. The black holes would still be massive, but the stellar mass would have increased proportionally. Feedback also affects the surrounding intergalactic medium. Gas expelled from galaxies does not disappear. It flows into the space between galaxies, enriching the intergalactic medium with heavy elements created inside stars. This enriched gas can later fall back into galaxies or feed star formation in other systems. The cycle of gas flowing in and out of galaxies connects the evolution of individual objects to the evolution of the entire cosmic web. Simulations of galaxy formation must include feedback to match observations. Early simulations that ignored black hole feedback predicted too many massive galaxies forming too early. Adding feedback physics brings the simulations into agreement with observations. The energy from black holes regulates galaxy growth across cosmic time. Webb is testing feedback models, by observing galaxies at different stages of evolution. Some show active outflows, others show no signs of feedback. By comparing these systems, astronomers can determine what triggers feedback and how long it lasts. These observations will refine theoretical models and improve our understanding of how galaxies form. But even as black holes sculpt galaxies in the early universe, they were also clearing away the cosmic fog itself. After the Big Bang, the universe glowed. Protons and electrons floated freely in a hot plasma that radiated light. As space expanded and cooled, the temperature dropped below 3,000 degrees. Electrons and protons combined to form neutral hydrogen atoms. The universe became transparent, but it also became dark. This period is called the Cosmic Dark Ages. No stars existed yet to light up the darkness. Neutral hydrogen filled all of space. This gas absorbs ultraviolet light efficiently, making the universe opaque at certain wavelengths. Any light trying to travel long distances would be absorbed by intervening hydrogen. Then the first stars ignited. Their intense ultraviolet radiation ionized the hydrogen around them, splitting atoms back into protons and electrons. Ionized hydrogen is transparent to ultraviolet light. Each star created a bubble of ionized gas expanding outward. As more stars formed, these bubbles grew and eventually merged. Within several 100 million years, the entire universe became ionized again. This transition from neutral to ionized is called reionization. It represents one of the major phase changes in cosmic history. Understanding when and how it happened reveals crucial information about the first stars and galaxies. Webb is designed specifically to study this epoch. The telescope observes galaxies from the reionization era at redshifts between 6 and 10. These galaxies existed when the universe was partially ionized. Some regions had been cleared by earlier stars. Other regions remain neutral. By studying these galaxies, astronomers can determine how many ionizing photons they produced and how fast reionization progressed. The challenge is that not all photons escape galaxies. Ultraviolet light can be absorbed by dust or neutral gas within the galaxy itself. Only photons that escape into intergalactic space contribute to reionization. Measuring the escape fraction is difficult but essential for understanding the process. Webb spectra reveal clues about escape fractions. Certain emission line ratios indicate whether ultraviolet photons are escaping or being absorbed internally. Galaxies with high escape fractions show specific spectral signatures. By identifying such galaxies, astronomers can estimate what fraction of early galaxies contributed significantly to reionization. Current observations suggest that most early galaxies have moderate to high escape fractions. This means they efficiently released ionizing photons into intergalactic space. Combined with the surprisingly large number of bright galaxies Webb has found, this suggests galaxies alone could have reionized the universe. Earlier theories proposed that exotic sources, like quasars or population 3 stars, dominated reionization. Webb data indicates ordinary star-forming galaxies did most of the work. The timeline of reionization remains uncertain. Most evidence suggests the process completed by redshift 6, about 1 billion years after the Big Bang. But exactly when it started and how long it took are open questions. Did reionization happen quickly in a few 100 million years, or did it proceed slowly over 1 billion years? Webb observations are constraining the timeline. By measuring the neutral hydrogen fraction at different redshifts, astronomers can map reionization's progress. Early results indicate the process accelerated around redshift 8. Before that, progress was slow. After that, the remaining neutral hydrogen disappeared rapidly. One puzzle involves the topology of reionization. Did the ionized bubbles grow uniformly in all directions, or did they follow the cosmic web structure? Simulations predict that ionized regions should preferentially expand along filaments where galaxies cluster. Voids would remain neutral longer. Testing this requires mapping both the ionized regions and the galaxy distribution simultaneously. Webb is beginning to provide such maps. Large surveys image and obtain spectra of thousands of galaxies across wide areas of sky. Combined with measurements of the intergalactic medium's ionization state, these data reveal how reionization unfolded in 3 dimensions. The emerging picture shows a patchy, complex process that varied significantly from region to region, and some of the tools for studying reionization come from an unexpected source. Einstein's theory of general relativity predicts that mass warps spacetime. Light traveling through warped spacetime follows curved paths. When a massive object like a galaxy cluster sits between us and a more distant galaxy, the cluster's gravity bends the light from the background galaxy. This bending can magnify the background object, making it appear brighter and larger than it would without the lensing. Astronomers call this gravitational lensing. It acts like a natural telescope, magnifying distant objects that would otherwise be too faint to study. Webb exploits gravitational lensing systematically to observe the faintest galaxies in the early universe. By pointing at massive galaxy clusters, the telescope gains access to galaxies behind them that are magnified by factors of 10 or even 100. One recent observation targeted a cluster called Abel S 1063. This massive collection of galaxies sits 4.5 billion light-years away. Its gravitational field distorts the images of more distant galaxies into arcs and multiple images. Webb captured hundreds of such distorted background galaxies in a single image. Some of these lensed galaxies date back to when the universe was less than 1 billion years old. Without the magnification from the cluster, they would be completely undetectable. Even with Webb's power, the unaided view would show nothing. The gravitational lens makes the impossible possible. Lensing also allows detailed study of individual galaxies. When a galaxy is magnified by a factor of 50, features that would normally be too small to resolve become visible. Astronomers can study the distribution of star formation within the galaxy, identify individual star clusters, and measure properties that would otherwise require much larger telescopes. One lensed galaxy observed by Webb shows 10 distinct star clusters. Each cluster represents a region where stars formed simultaneously from a collapsing gas cloud. The clusters have different ages, indicating that star formation occurred in multiple bursts rather than continuously. This level of detail is only accessible because gravitational lensing magnified the galaxy enough to resolve its internal structure. The amount of magnification depends on the alignment. If the background galaxy sits directly behind the center of the lensing cluster, the magnification can be extreme. Slight misalignments produce less magnification but still help significantly. Astronomers model the cluster's mass distribution to calculate the exact magnification factor for each background object. Gravitational lensing also reveals information about the lens itself. The distortion pattern depends on how mass distributes in the cluster. By analyzing the shapes and positions of lensed galaxies, astronomers can map the cluster's total mass, including its dark matter. This provides an independent measurement of dark matter properties. Some clusters produce multiple images of the same background galaxy. Light from the galaxy takes different paths around the cluster, arriving at Earth at slightly different times and from different directions. Astronomers see the same galaxy in 2, 3, or even more positions in the sky. By comparing these images, they can test general relativity and constrain the cluster's mass distribution with high precision. Webb has observed dozens of massive clusters as gravitational lenses. Each observation reveals hundreds of lensed background galaxies. The cumulative result is a dataset of thousands of extremely distant galaxies, many magnified enough for detailed study. This sample is revolutionizing our understanding of galaxy formation in the first billion years. One particularly powerful application combines lensing with spectroscopy. Webb obtains spectra of lensed galaxies, measuring their chemical composition, star formation rate, and ionization state. The magnification makes it possible to study galaxies that would be far too faint for spectroscopy without lensing. These measurements provide unprecedented insight into the properties of typical galaxies during reionization, and some of the lensed galaxies show unexpected characteristics. The galaxy appeared as an elongated arc in Webb images of a massive galaxy cluster. Gravitational lensing had stretched and magnified it. Astronomers nicknamed it the Firefly Sparkle because of its appearance. When they examined it closely, they found something remarkable. The galaxy contained 10 distinct, bright star clusters, each clearly resolved in Webb's images. This galaxy existed about 600 million years after the Big Bang. At that time, the universe was less than 5% of its current age. Most galaxies observed at this epoch appear as single, compact blobs. Firefly Sparkle showed clear internal structure. The star clusters stood out as individual bright points arranged in a line. Measuring the properties of each cluster revealed that they have different ages and masses. Some contain young, hot stars just a few million years old. Others have slightly older populations. The clusters range from a few thousand to several 100,000 solar masses. Together, they total about 10 million solar masses of stars. This total stellar mass is surprisingly low for a galaxy. The Milky Way contains over 100 billion solar masses of stars. Firefly Sparkle has less than 1/10,000th of that. Yet this lightweight galaxy might resemble what the Milky Way looked like at a similar age. Both the timing and the mass match predictions for our galaxy's early state. The discovery demonstrates that massive galaxies, like the Milky Way, built up gradually from much smaller systems. Firefly Sparkle is not a fully formed galaxy. It is a building block, a proto-galaxy in the process of assembling. Over billions of years, systems like this would merge with others, growing into the massive galaxies we see today. The 10 star clusters provide a snapshot of star formation in action. Each cluster formed from a collapsing gas cloud. The fact that they have different ages shows that star formation did not happen all at once. Instead, it occurred in bursts separated by millions of years. Gas accumulated in the galaxy, triggered star formation, and then perhaps blew out or heated up, pausing star formation until more gas arrived. This episodic star formation might be common in early galaxies. Gas flows into the galaxy along cosmic web filaments irregularly. When gas arrives, it triggers a burst of star formation. Feedback from the newly formed stars then heats the gas and prevents further star formation temporarily. The cycle repeats each time new gas accumulates. Without gravitational lensing, Firefly Sparkle would have been impossible to study in detail. The magnification factor of about 30 made the galaxy bright enough for Webb to resolve individual star clusters. This demonstrates the power of combining gravitational lensing with Webb's capabilities. Together, they provide a microscope for examining the early universe. Other lensed galaxies show similar clustering of star formation. It appears that many early galaxies form stars in distinct regions rather than smoothly throughout their volume. This clumpy star formation might reflect the turbulent conditions in early galaxy gas reservoirs. Instabilities cause gas to fragment into dense clumps that each form a cluster of stars. The clusters themselves might be the precursors of globular clusters, ancient star clusters that orbit most large galaxies today. Globular clusters contain hundreds of thousands to millions of stars packed into spherical regions just a few dozen light-years across. Their ages indicate they formed in the early universe. Firefly Sparkle's star clusters have similar masses and might evolve into objects resembling the Milky Way's globular clusters. Studying galaxies like Firefly Sparkle connects the distant past to the present. By understanding how small protogalaxies assemble and form stars, astronomers learn how systems like the Milky Way came to be. We are seeing our own history written in the light from these ancient objects. Yet, even as galaxies build themselves from star clusters, the raw materials for planets and life were being forged. Stars form from collapsing clouds of gas and dust. The The cloud flattens into a disk as it rotates. The star ignites at the center, and the disk surrounds it. This disk contains all the material that will eventually become planets, moons, asteroids, and comets. Understanding the disk's composition reveals what building blocks are available for planet formation. Webb observed a young stellar system and detected crystalline water ice in its disk. This form of ice has a regular molecular structure, like ice in a freezer. It differs from amorphous ice, where water molecules arrange randomly. The presence of crystalline ice indicates specific temperature and pressure conditions in the disk. The ice sits far from the central star, in the cold outer regions where temperatures drop below freezing. Webb's spectrum showed distinctive absorption features at specific infrared wavelengths that match crystalline water ice. The signal is unambiguous. The disk contains abundant ice in the region where giant planets might form. This discovery matters because water is essential for life as we know it. Rocky planets forming in the inner disk start out dry because temperatures are too high for ice to exist. Water must be delivered later, either by comets or asteroids that formed in the outer disk and then migrated inward. The ice Webb detected represents the reservoir that could eventually supply water to inner rocky worlds. Giant planets also require water ice. Current models suggest that Jupiter and Saturn formed when icy cores grew large enough to gravitationally capture surrounding hydrogen and helium. The cores built up from collisions of icy planetesimals, solid objects ranging from meters to hundreds of kilometers across. The abundant ice Webb detected provides exactly the material needed for this process. The crystalline structure tells us about the disk's history. Amorphous ice forms when water vapor freezes rapidly. Crystalline ice requires either slow freezing or a period of warming that allows molecules to rearrange. Finding crystalline ice suggests the disk has experienced thermal processing, perhaps from shock waves or radiation from the central star. The observations targeted a disk around a star similar to our home star. This makes the findings directly relevant to understanding solar system formation. If ice was abundant in the solar nebula, then the process Webb is observing might mirror what happened 4.6 billion years ago when our planetary system formed. Other disks, observed by Webb, show similar ice features. This suggests that crystalline water ice is common in planet-forming disks. Most planetary systems likely have access to substantial amounts of water during formation. This increases the probability that rocky planets in habitable zones could acquire water and potentially develop conditions suitable for life. The amount of ice matters as much as its presence. Too little ice, and giant planets might not form. Too much, and the disk might fragment into multiple cores that compete for material. Webb measurements of ice abundance in multiple disks will reveal whether there is a typical amount or if it varies widely from system to system. Beyond water ice, disks contain other ices. Carbon dioxide, methane, and ammonia all freeze at temperatures found in outer disk regions. Webb has detected these ices in some disks. The mix of different ices affects planet composition. A planet forming from ice-rich material will have a different chemistry than one forming from rock-rich material. These observations connect star formation to planet formation to astrobiology. The ices in planet-forming disks determine what raw materials are available. The planets that form inherit their compositions from the disk. Rocky planets in habitable zones might acquire water, atmospheres, and organic compounds. Some of those planets might eventually develop life. Webb is cataloging the ingredients across many stellar systems. By the end of its mission, astronomers will have a statistical understanding of how common different disk compositions are. This will constrain theories of planet formation and help predict what kinds of planetary systems exist throughout the galaxy. And while Webb studies the formation of new systems, it continues observing the deaths of old stars. The gamma-ray burst lasted 8 seconds. In that brief time, it released more energy than the home star will emit over its entire 10 billion-year lifetime. The explosion hurled jets of material outward at 99.99% the speed of light. When one of these jets pointed toward Earth, detectors across the world recorded the flash. This particular burst came from the early universe. The gamma rays traveled for more than 13 billion years before reaching Earth. By the time Webb observed the afterglow, the explosion was already ancient history, yet the observation revealed details about stellar death during the first billion years of cosmic time. Gamma ray bursts come in two types. Short bursts lasting less than 2 seconds originate from merging neutron stars. Long bursts lasting more than 2 seconds come from collapsing massive stars. The 8-second burst Webb studied clearly fell into the long category. This was a massive star dying. The mechanism involves core collapse. When a star more than 20 times heavier than our home star exhausts its nuclear fuel, the core can no longer support itself against gravity. It collapses to form a black hole. Material falling toward the black hole forms an accretion disk. Magnetic fields threading the disk launch jets perpendicular to the disk plane. These jets punch through the collapsing star, emerging from the stellar surface at relativistic speeds. The intense energy heats the jet material to billions of degrees, producing gamma rays. As the jet continues outward, it sweeps up surrounding material, creating a shock wave that radiates across the electromagnetic spectrum. Webb observed this burst at multiple wavelengths. The infrared spectrum showed emission lines characteristic of heavy elements. Silicon, oxygen, and iron appeared in the spectrum. These elements formed inside the dying star through nuclear fusion and were expelled during the explosion. Webb was analyzing the star's innards, spread across space. Finding heavy elements in the spectrum indicates that even early universe stars produced them. This might seem obvious, but it was not guaranteed. Very low metallicity stars might die differently, perhaps without producing as many heavy elements. The fact that this ancient burst shows similar enrichment to modern supernovae suggests the underlying physics has not changed. Gamma-ray bursts also serve as probes of the intergalactic medium. Light from the burst passes through gas between the explosion and Earth. This intervening gas absorbs certain wavelengths, leaving imprints in the spectrum. By analyzing these absorption lines, astronomers can study the composition and density of intergalactic gas billions of years ago. The observations revealed neutral hydrogen absorption, indicating the burst occurred during or near the end of reionization. Some neutral hydrogen still existed along the line of sight. This constrains when and where reionization completed. Different lines of sight to different gamma-ray bursts will map the patchiness of reionization across the sky. Gamma-ray bursts are rare, only about 1 per galaxy every million years. But in the observable universe, hundreds occur every day. The challenge is catching them quickly and observing before the afterglow fades. Ground-based telescopes can alert Webb within minutes of a detection, triggering rapid observations. These rapid response observations capitalize on Webb's flexibility. The telescope can interrupt scheduled programs to observe transient events. For gamma-ray bursts, speed is essential. The afterglow fades rapidly, dropping to undetectable levels within days. Webb must observe within hours to capture useful data. Each gamma-ray burst observed at high redshift adds to our understanding of massive star death in the early universe. The sample is growing. Within a few years, Webb will have observed dozens of distant bursts, providing statistics on their properties and surrounding environments. This will reveal how the deaths of the first massive stars enriched the cosmos and triggered subsequent generations of star formation. But the discoveries continue pushing deeper into time. Every few months, astronomers announce a new distance record. The most distant galaxy known keeps getting more distant. Each new record holder existed earlier in cosmic history, closer to the Big Bang. The progression shows Webb pushing the frontier of observable time steadily backward. JADES held the record at redshift 14.32 for several months. Then another galaxy was confirmed at redshift 14.5. A few months later, a candidate appeared at redshift 16. Spectroscopic confirmation is pending. If real, this galaxy formed just 250 million years after the Big Bang. Why does the record keep advancing? Partly because Webb is still young. Astronomers are analyzing data from its first few years of operation. As they work through the observations, they find fainter and more distant objects. The deepest images require tens of hours of exposure time. Not all deep fields have been observed yet. More are scheduled. Advancing technology helps too. Analysis techniques improve as astronomers gain experience with Webb data. Machine learning algorithms scan images, identifying candidate high redshift galaxies that humans might miss. Spectroscopic follow-up confirms or rejects these candidates. The process is becoming more efficient. There is also statistical inevitability. If bright galaxies exist at redshift 14, even brighter ones probably exist at redshift 15. Galaxies form continuously, and the earliest ones are simply the rarest. Search a large enough volume of space, and you will find them. Webb is searching that volume. The distance record cannot advance forever. Eventually, we reach the epoch of the first stars. Before redshift 20 or so, no stars existed. The universe was too young. Going beyond redshift 20 means looking at the dark ages, when only neutral hydrogen filled space. Webb might detect faint emission from this hydrogen, but it will not find galaxies. Between redshift 14 and 20 lies unexplored territory. Webb has found galaxies at 14. Theorists predict galaxies should form by redshift 15 or 16. The gap between prediction and observation is narrowing. Within the next few years, Webb will likely discover galaxies in this range, extending our view to cover 98% of cosmic history. Each record-breaking galaxy teaches us something. The brightness reveals star formation rates. The spectrum shows chemical composition. The size indicates how structure forms. Together, these measurements constrain models of galaxy formation. Each new galaxy either confirms predictions or forces revisions. Some early galaxies appear surprisingly ordinary. They form stars, contain some heavy elements, and have sizes consistent with models. Others are extreme outliers. Too bright, too massive, too enriched. These outliers are the most interesting because they challenge our understanding. They indicate physics we do not fully grasp. The record holders also grab public attention. People find it fascinating to see light from near the beginning of time. Images showing galaxies from the first few 100 million years make the abstract concept of cosmic history tangible. You are looking at photons that have traveled for 13 billion years to reach your eyes. But behind the distance records lies a deeper mystery about the universe itself. The universe is not just expanding, the expansion is accelerating. Galaxies are moving away from each other faster now than they were billions of years ago. Something is pushing space apart with increasing strength over time. Astronomers call this mysterious force dark energy. Dark energy was discovered in the late 1990s using observations of distant supernovae. By measuring how bright these explosions appeared, astronomers determined their distances. Comparing distance with redshift revealed that the expansion rate has been increasing. The universe was decelerating for the first several billion years, slowed by gravity pulling matter together. Then, about 6 billion years ago, dark energy began to dominate, and the expansion started accelerating. Webb observations confirm and refine these findings. By studying more supernovae at higher redshift, Webb extends the measurement of cosmic expansion history further back in time. The data show that dark energy has been present for billions of years, consistently causing acceleration. What is dark energy? Nobody knows. The simplest explanation is that it is a property of space itself. Einstein's equations allow for a cosmological constant, an energy density that remains the same as space expands. This means that as the universe grows, more dark energy appears because there is more space. The total energy increases, driving faster expansion. This sounds like it violates energy conservation. In a sense, it does. But general relativity allows this, because energy conservation works differently in curved spacetime. The expansion of space can create or destroy energy without violating the equations. Dark energy is one manifestation of this strange behavior. Measuring the properties of dark energy is a major goal of modern cosmology. Is it truly constant, or does it change over time? If it changes, the rate of change constrains theoretical models. Webb observations provide data points at different cosmic epochs, tracking how dark energy behaved over billions of years. Current measurements suggest dark energy has been remarkably constant. Its density does not appear to change significantly as the universe evolves. This matches the simplest models but leaves the fundamental nature of dark energy unexplained. A cosmological constant fits the data but does not tell us why it exists or why it has the specific value we measure. Alternative theories propose that dark energy is not a constant property of space, but a dynamic field that evolves. Some models predict that dark energy should be stronger or weaker at earlier times. Webb measurements will test these predictions. So far, no clear deviation from a constant has been detected. The future of the universe depends on dark energy. If it remains constant, the expansion will continue accelerating forever. Galaxies outside our local group will recede faster and faster, eventually moving away faster than light can travel toward us. They will disappear beyond the cosmic horizon, forever unreachable. The universe will become increasingly dark and empty as stars burn out and are not replaced. If dark energy increases over time, the acceleration could become so extreme that it tears apart galaxies, stars, and eventually atoms. This scenario, called the Big Rip, would destroy all structure in the universe. Current measurements give no indication this will happen, but the possibility exists. If dark energy decreases, the expansion might eventually reverse. Gravity would take over, pulling everything back together in a big crunch. The universe would collapse to a singularity, potentially followed by a new Big Bang. This cyclic model is speculative and not favored by current data. Webb contributes to dark energy studies by providing precise measurements of cosmic expansion at different times. These measurements, combined with data from other telescopes and experiments, will eventually reveal whether dark energy is truly constant or evolves. Understanding dark energy is one of the deepest questions in physics. Yet, even with all of Webb's power, there are limits. Webb is the most powerful telescope ever built, but it cannot see everything. There are limits. Some objects are too faint, some are too distant, some emit light at wavelengths Webb cannot detect. The first 200 million years after the Big Bang remain largely hidden, just beyond the edge of what Webb can reach. Galaxies from this earliest epoch would have redshifts above 20. Their light has been stretched so far into the infrared that even Webb struggles to detect them. The galaxies would also be small and faint, having had less time to form stars. Detecting them requires extremely long exposures, and possibly gravitational lensing to provide magnification. Webb has the technical capability to find galaxies at redshift 20 if they are bright enough, but brightness depends on star formation rate and mass. Early simulations predicted the first galaxies would be tiny, with masses of just a few million solar masses. Such objects would be far too faint for Webb to detect without extraordinary lensing. However, if the first galaxies formed stars more efficiently than models predict, they might be bright enough to see. This is plausible given that early galaxies have consistently been brighter than expected. If the trend continues to earlier times, galaxies at redshift 20 might be detectable after all. Another challenge involves contamination. At these extreme redshifts, distinguishing real high redshift galaxies from other objects becomes difficult. Certain types of cool stars in our own galaxy can mimic the colors of distant galaxies. Spectroscopy can differentiate them, but obtaining spectra of the faintest candidates requires enormous amounts of telescope time. The James Webb Telescope will operate for at least 10 years, possibly longer if fuel reserves and instruments remain functional. During its lifetime, it will conduct deeper and deeper observations, pushing closer to the epoch of the first stars. Future telescopes might eventually peer beyond Webb's reach, but for now, it represents the frontier. What could surpass Webb? Larger ground-based telescopes with adaptive optics are under construction. These will have greater light-collecting power in some wavelengths. However, Earth's atmosphere absorbs much infrared light, limiting ground-based infrared astronomy. For the most distant galaxies, space-based infrared telescopes remain essential. The next generation of space telescopes is still being planned. Concepts include telescopes with mirrors twice the size of Webb's or arrays of telescopes working together. These facilities would extend observations to redshift 25 or beyond, potentially imaging the very first stars. But they will not launch for decades. In the meantime, Webb is transforming our understanding of the cosmos. Every observation reveals something unexpected. Black holes too massive for their galaxies, galaxies too bright for their age. Star formation proceeding differently than models predicted. Structures emerging earlier than thought possible. These discoveries do not break cosmology, they expand it. Our models were too simple, our predictions too conservative. The universe is richer and more complex than we imagined. Webb shows us the reality, and our theories must adapt to match. We are living through a golden age of astronomy. Never before have we seen the early universe so clearly. Never before have we watched galaxies forming just after the Big Bang. Never before have we probed the depths of stars billions of light years away, or examined the internal structures of distant stellar nurseries. James Webb has uncovered the true scale of the universe, and it is vaster, stranger, and more magnificent than anyone predicted. Every week brings new discoveries. Every observation challenges something we thought we understood. The cosmos is not finished revealing its secrets. The telescope will continue observing, pushing deeper into time and space, showing us wonders we have not yet imagined. This is not the end of the story. This is only the beginning. Webb has opened a window to cosmic dawn, and we are still learning what we see through it. The universe waited 13.8 billion years to be discovered. Now, finally, we are looking back to the very edge of time itself.